implement, okay, depth first traversal. That we can use either recursion to develop depth first traversal, okay, or we can use iterative. In other words, we use the loop, okay, to develop it. Let's see, do I have picture? No. Because today we're gonna do that lecture, the lab, depth first traversal. Okay. Yesterday we look at the first traversal that where is it? Oh, we still have a lot to learn. This one, remember the first traversal that we did in the class on last Friday. Okay, and then on Tuesday that we switched the class. Oh, but before that, do you know that the class had been changed? Okay, I already announced, but many of you already forgot that on Wednesday and Friday we will not have a class at 2 o'clock. Okay, we moved to a class on Tuesday at 4:30 and also Friday at 4:30. Because on last Tuesday, many of you missed the class. Okay, but we already changed the schedule. Okay. So again, on Tuesday we learn this one, but we not learn how to do this one, but we learn how to implement in Java. Okay. One way we can use recursion. Okay. To do this. Okay, because to be able to do the depth first traversal. Okay, when we keep going down, we have to be able to go back. Okay, like for example, here when we go to the 23, we need to go back to 25 and go down 27, because the depth first keep going down. Okay, like when we go down to the 15, we have to go back to 20. For example, like in order to visit 10, after 10 visit 15, after that you have to visit the parent. Okay, of this left subtree, which is a 20. So we have to go back. To be able to go back, okay, we use the stack mechanism, because the stack, the node that you just visit, if you want to come back, okay, you push in the stack first. Okay, so for example, post order means visit the parent at the end. So you're not going to visit 20. 20 is supposed to be visited at the end, because 20 is the root node, is a parent of everything. Okay, it's ancestor. Okay, so we have to have somehow, somewhere to go back to the 20, to the root. However, this will be the last one. Okay, so stack mechanism can help us implement it. Okay, you want to visit this one for the last thing. Okay, we start from the root, but we will not visit this one. We try to visit everything from the left. Okay, we try to visit this one. Okay, this one. And for example, post order, you're going to finish this one first, and then go back, but not visit that one. Go down here, and visit this. And after visit this, you go to the parent, visit that. Now visit this with the parent. And you can see that we have been visit 25, 27 before visit 26. So we have to go back to 27, back to 25, back to 30. And that's just like stack. The node that you visit first, okay, the node that you check first, we will come back to that node. So we use the stack to push. We push 20 at the bottom, push 30 on top of 20, put 25, put 27, okay, put 26. After that, we visit 26, visit 27, visit 25, visit 30. That's the stack mechanism. And we know that the recursion use stack. Okay, so instead of writing that, we just do the make recursive call. Recursive call using stack mechanism. Because recursive call, the one who, the caller will be pushed in the stack, and then they call another one, the callee. Okay, so if we use the recursion, we can solve this. Another way, we don't use recursion, we use a loop. Okay, but again, this loop, we can use the stack to keep it, okay, in the stack by ourselves. Okay, we will not visit. Ah, okay, can you hear me? I didn't talk loud enough. Okay. This is what we have learned on Tuesday. Okay, I cannot explain the whole thing, but the idea is, okay, for example, this one do pre-order. Okay, so the idea of pre-order is to visit parent first and then go down to the child, left first and then go to the right. Okay, after visit the whole left subtree, then we go to the right subtree. Okay, so to do that, okay, to be able to go to the right subtree, we need to be able to get back to the parent first and then we move parent dot right. Okay, so before to do that, we need to have a stack to keep track of the parent. Okay, so that's why this one, okay, every time we visit that node, okay, after we visit that node, this is a pre-order, visit parent first. We visit that node. After we visit that node, we're going to push the right in the stack, right child, okay, and push the left child in the stack. Okay, and then after that, when we come back, since we push left later, the left will be on top of the right in terms of stack. We push right first, okay, the right of the right node. We have okay, we push the right first and push left later. So for this case, 30 will be at the bottom and then 10 will be on the top. And then after that, the loop will go back and pop the 10 out to visit the 10. Okay, if 10 have the right child, we're going to push 15 for this case. So you can see 30 is still there. After we pop 10 out, visit the 10 and we push 15 on the top. So 15 on the top and 30 at the bottom. If we come back to this stack, 15 is going to be visit first. Okay, and then 30 visit later. Okay. The idea of pre-order is that, for this example, okay, is that when we have a tree, okay, we start from the root, okay, and we want to make sure that we will come back to visit the right child. Okay, but to make it simple, they push the right child in the stack and put the left child. Okay, when the loop come back to the top, we will pop that whatever on top of the stack out and visit that node. If the left child have, okay, if the node that we're visiting have their own right child, left child, so when we're going to put right child, left child, okay, and then later on come back, we'll pop the left child out and visit that left child. If that left child have their own children, so then we're going to do the same thing. Put the right child, put the left child. So you can see that the right child keep remaining, but the left child that we push, we're going to be popped in the next loop that we go. Okay, so we visit that node, and later on we're going to visit the left child. If no left child, then we're going to visit the right child. Understand? Yes or no? No, okay. Let's say we have this tree. 15, 30, 100, 70, okay, 190, 120, okay, 55, okay, 80, 10, 40, for example, okay. Let's say we use this loop, okay, we're gonna start from the root, okay, and then if the root, okay, we start from the root, okay, and then we're gonna check whether we have right and left child or not. If we have right child, we're gonna push the right child, but this case is 100, and the right child 50. Later on, we're gonna push the left child 30. Okay, so that next time when the loop to come back to the top, they're gonna pop this 30 out and visit the 30. If the 30 have right child, left child, we're gonna push right child first, and then push left child later. And you can see that after we visit 30, we're gonna visit 10. Later on, visit 40, we pop it out, and then visit 100 later. Okay, you can see the 100 will be visit after 40 and after 10, which is in terms of pre-order. We're going to visit parent, left child, one is a parent before left, right. All of this going to be visited before that one. Understand? Okay. So if we work on the whole thing, okay, so actually, yeah. Anyway, oh yeah, is that chemical or just water? So is using this, okay, algorithm. They're gonna start from the root. Okay, from the root. Okay, first thing we do, if the root is not empty, it means it's not empty tree. We're gonna start pushing the root first. Okay, so actually from the beginning, we can start push 50 first with the root. Okay, start from the top. Okay, make P point to the root. Root is not now. We're gonna start pushing the P, which is the root at this time. Okay, P start from the root. Okay, and then push 50 in there. Okay, let me write the stack in here. Okay, hey, yeah. How this thing work? Oh, I break it. Anyway, okay, start from 50. Okay. Okay, P start at 50. Okay, we push the P. After we push the P in the stack, now we're going to make a loop. Okay, as long as the loop is not empty, we do this. Okay, so we're going to pop this 50 out and visit the 50. Okay, after we visit 50, we check whether we have right child or left child or not. If we do have them, we push them. Okay, so we push 30. Okay, sorry, put right child first. Right child is 100. Okay, so we push 100. After we put the right child, then we put the left child, right, left. Okay, and then after that, we're going to go back to the top of the loop. If we go back to the top of the loop, we pop. What is on the top is 30, which is the left child of the 50. Okay, so that's why we visit 30. After we pop, we visit. Pop, visit. And then put the right and left in there, which is the 40 and then 100, right, left of 30. Right now, the P is here. Okay. After that, we're gonna pop. Okay. Then we have 100 on top, so we pop 100 out. It means I move P here. Okay, but after I move P here, I visit this node 10. After I visit this node, since 10 has no left right, so nothing to push. Okay. So I'm gonna go back to the top of the loop. I'm gonna pop. So if I pop 40 out. Okay. After I pop 40 out, my P gonna point to here. Okay. So I'm gonna visit this 40. After I visit 40, I try to put right child, left child of 40, but it is no child at all. Okay. So then I'm gonna continue pop. So what I'm gonna pop here? Okay, so I'm gonna pop this 100. Okay, my P gonna point at 100, and I'm gonna visit this P. After I visit, I'm gonna push right left of this node, which is 190 and 70. Okay, so after I put one right first and then left later, right of P and left of P that I push. Okay, again we put right first because in terms of pre-order we visit left first, visit right later. Okay. But again, you will see later on is 90 in terms of pre-order. Not going to be visit until we finish everything on the left subtree. Okay, you're going to see later on, okay, because you can see this mechanism. So after we put right, left, then we're going to go back to the top of the loop, pop. When we pop 70 out. So my P is going to point at 70. Okay, after my P point at 70, I visit this P. After I visit, I'm going to push right left of this P, which is 80 and 55. And you can see that right now, 55 and 80 is on top of 190. Like I said, this one been pushed first, it's going to stay at the bottom. This one going to push their children on top of it. So it means we're going to finish the left subtree before we're going to go to the right subtree. If this one have further more children down here, that one going to be at the bottom of the stack for a while. Until I finish everything here, then this one going to be popped. Understand? Okay. Okay, for this case, after I push 80 and 55, which is the children of 70, on top of the loop, okay, I'm going to pop this one out. So I pop 55, make P point to that one, P equal to the pop, visit this P, and then try to push right left of 55. But since this one have no right left, so nothing to push. Go to the top of the loop, pop again. So I pop 80 out. When I pop, my P move. Okay, and then after that, no right child, left child, so nothing to push. And then now, since you can see that if I pop, I'm going to pop 190 again. At this time, we already finished everything on the left. Okay, that's why the right child to start. Okay, so I'm going to pop 190, make P point to the one that I pop, and visit that P 190, and then going to push right child, left child. But since this one have no right, that's an example, so then I visit push the left only. Okay, and then now I go back to the top to pop, so I pop this one, pop 120, my P point here, and then I visit 120. Okay, and then after that, there is no right child, no left child, 120. So I go to the top of the loop. Now in the top of the loop, nothing else to pop. Okay, the stack is empty now. And say it's empty, the whole thing stops. And now you can see this is the pre-order. Okay, visit parent and left and right. 50 is the parent node of all these left subtree. This is the right subtree of 50. Understand? Okay. It is using loop. Okay. But again, you don't have to use loop. You can use the recursion. They can do something like this for us. Okay, without dealing with anything, just the concept of recursion. Okay, recursion Z. Okay, we're gonna come back to the caller. Okay, let's say for example in the pre-order, we visit that node, and then we're gonna make a recursive call pre-order on this node, because the pre-order have parameter of one node. Okay, so we start from the root. Okay, the root we're gonna visit that node. After visit this node, we're gonna make a recursive call pre-order of left. Okay, and again, when I call pre-order of the left left node, okay, of this parent, okay, this whole thing here that the caller will be pushed in the stack, and we're gonna start doing this one. And this is the recursive call. They're gonna go pre-order of this one, visit this one, and reorder recursive call pre-order for left child. Okay, and recursive call gonna do the same thing. Visit this one, make a recursive call for left child, which is a null. Okay, when I make recursive call for a null, it will do nothing. Make a recursive call for the right of this one, also null, do nothing. So when both of them finish, left, right, now this the whole thing finished. When the whole thing finished, they call to the caller. Who called this one? Is a note 30. Note 30 call pre-order of this note 10. Okay? So 30 is the one that called pre-order of 10. So after 30, okay, already visit, already pre-order of this note 10, now they're going to call pre-order of the right of that note, which is 40. Okay? And this one going to visit 40, try to visit left, which is the now, try to visit right, the now, do nothing. And then after this one finished, it means the 30 already finished left, finished right. After the finish of this, it means the whole thing finished. This is the whole thing of 30. The whole thing of 30 finished, it means the left of 50 finished. Because pre-order of 50 is the one that call pre-order of 30. Okay? So when pre-order of 30 call by 50, okay, when this one finished, we're going to call pre-order of the right of P. Right now P 50, they're going to call pre-order of 100. And continue the same thing. Okay? That's the recursion version of the depth first traversal. Okay? So to do this lab, okay, you need the basic 3, which is insertion. Okay, number 1, we already did this one last week. Do you have it or not? Okay, if you do have it, you continue from last week. That is what we did last week. Okay, everybody still have this one from last week? Who doesn't have this one from last week? Then you have to go to classroom on demand and copy this one. Everybody still have my file or not? What we did last week, anyone doesn't have this one? Everybody have this code? The one that worked? Anyone doesn't have this? Go to classroom on demand. You have it? Can I continue from last week? From the binary search tree. If you cannot, you go to classroom on demand. I have these 3 files. Okay, the main program, the binary search tree, and the node. Okay, it's still runnable? Your program, yes or no? Okay, can I continue? Yes or no? Yes? Anyone doesn't have these 3 files? Bonus? Okay, I'll help Bonus. Give her a copy. Did she come last week? Okay, anyone who already have this? Red, right, the depth first traversal using this maybe recursion first, simple version. Go to binary search tree. We're not gonna do anything else. We're not gonna do something that we did. Okay, like insert this thing. We don't do anymore. Okay, yeah, we did last week. Now we're gonna do a new method. Okay. Then we're gonna do the pre-order traversal. Okay, bypassing the node and the P. Okay, what in order traversal? And you write by yourself using recursion. Here. Pre-order, visit first, and then make a recursive call left, call right. In order, recursive call left first before visit, and then recursive call on the right node. Post, visit the parent at the end. So then we recursive post order 2 times on the left and the right, and then visit the parent after. This is the post. Okay, so if P is not equal to now, okay, good. What we do? Visit. How can we visit? Okay, system dot out dot print line. Okay. Okay, just print this P. P dot, what do we have? Maybe we show only the name. Okay, fine, name. Okay, maybe look like ID because the way we order the tree in terms of, where's my main program here? In terms of binary search tree, we use the ID, right? To be in the order, remember? Okay. So let's just show ID. Okay. So far, I don't remember what my tree look like. What my tree look like, I forgot. Look like the one I draw last week, right? What my tree look like from here? If you have my tree here. What this tree look like? I already have 10 and they have 50 on the left, 75 on the right of 50. I insert 25, right? 25. 25 will be on the left of 50, good. And then later on, I insert what? 35, right? 35. Okay, according to my order of insertion. I insert 35 after 25. 35 will be where? On the 35. If it is my tree, 100 at the root, 50 is the left of 100. 50 is the left of 100. And then 50 have 2 children, 25 and 75. So if I insert 35, where would 35 be? 35 less than 100, less than 50, but greater than 25. Right? My 35 will be here on the right of 25. Okay? If I insert 80, 80 is less than 100, greater than 50, greater than 75. 80 will be somewhere on the right of 75. Okay? Oh, I insert 40 first, sorry. I insert 40 after 35. 40 is less than 50, greater than 25, greater than 35. So actually 40 is on the right of 35. And then insert 80. Insert 98 would be here. Right? Insert 200. 200 will be here. On the right 100. Agree? And then insert 199. 199 will be on the left of 200. And then insert 288 will be here. Agree? And then insert 1. 1 will be here, left of 25. Agree? This is what our tree look like. 100 have 2 children, 50 and 200. Okay? And then 50 have 2 children, 25, 25. 200 have 2 children, 199, 288. Okay? 25 have these 2 children, 75 have only 1 child, 35 have 1 child, 80 have 1 child. Okay? According to what we did last week. Yes or no? Okay, according to the insertion statement, I'm going to have these 3. Can you see my slide? Okay? Can you see what I have? Okay? Now, show me what did pre-order look like. If you do pre-order, what would the result be? Okay, I'm going to make this one out so then you can see clearly. Okay, if I do pre-order, what is going to print? What is going to be? 100 and then 50. Ooh, 200? No, you have to finish the left 3 of 100 first before go to right 3 of 100. 25. 1. Pre-order, parent first. 35. 40. And then right of 50. 80. 98. 200. 99. Okay, it's supposed to get this result. If we get this result, our program correct. Okay, how about in order? 1. Agree that in order. In order means left first, after you finish the whole left sub 3, then visit that node. Left, parent, right. Okay, bonus, fourth order. Wrong. Finish the children first before to the parent. You cannot visit 35 without visit 40 first, right? 40 is a child of 35. Parent have to be at the end, post order. So 1 and then 40 or not? 35, 25, 98, good, bonus. Okay? Are you with me? Okay. All right, now we're gonna make a recursive call. We're gonna write the recursive version of pre-order. Okay. If P is not now, we're gonna visit this node, right? Pre-order, visit the parent first. I'm gonna show ID. And then what? Recursive call. Pre-order, recursive call itself. Okay. To return. Okay, let me finish it. And then who next? P dot left. Okay, and then recursive call pre-order P dot right. Okay, then in the main program we're gonna call what the name of our tree? My tree, right? My tree dot pre-order. What do we pass? We start from the root, so we're gonna start from what the root of this tree? My tree dot root. Okay. So here is the result. Oh yeah. Maybe not in the no ln. Otherwise hard to see. Okay, so here it is a pre-order. Okay, the same thing that we put on it here. Are they the same? There, little one, binary is a 3. I mean the traversal. Okay? Run your program and let's see you get the same result. Here, this is the pre-order in binary search 3. The code is exactly the same. How come you have error? There is no visit. It just print it. System not out of print line. It is the visit. Visit, actually you do whatever you want, but I just print. Sun Thai. Finish? Do in order, post order by yourself in 1 minute. No. Everybody work on pre-order? Yeah? Okay, do in order by yourself, post order by yourself in 1 minute. You can just copy pre-order. Tuk tuk. Switch the plate. Tuk tuk. Done. It's the same. It just switch the place of the visit. We recursive call left first and then visit. Or recursive both left and right and then visit. If you understand recursion, write code is very easy. But performance is something else. And then go to main program, call them. In the main program, call in order, call post order from your my tree. Finish. If your program correct, okay, you should have the answer just like this one, right? The my main program, just like this one. In order, fourth order. Huh? No, no. Hai hénโตแล้วไม่ต้องเสียใจชีวิตล้มแล้วต้องลุกมัวแต่เสียใจอยู่ทำไมฟ้าจะร้องใครจะตายไม่เกี่ยว Finish, everyone. Get this result. Then you run. Okay, so it is in order and fourth order. in pre-post. Okay? Now, fun part is not this one. Fun part is without the recursion. Okay? Again, we can use the stack to help us. Again, the recursion. The disadvantage of recursion is have so much memory to keep pushing a lot of things in the method. Okay, so you can implement without recursion. Okay, by use this loop instead. Okay, can you write this one by yourself? Okay, I'll write by yourself. Okay, I start for you. Okay, another version of pre-order. Okay, Okay, I'm gonna minimize it. Okay, nothing much. Public void pre-order. Let's say recursion. Not recursive. Loop or iterative. Okay. This one we don't need to pass parameter. We're gonna make the tree to call this one, and this one will make their own stack. Stack st equal new stack. Then Java have stack already. We just call it tung. Okay. Stack from java.util. Okay. Just import. Okay. Don't write stack by yourself. We already have it. Okay. What should we do? Do by yourself. According to this code. Write it by yourself. Almost the same. My stack called ST. This one called travel stack. Just the name. The visit use print. Okay, use print for visit. That have pop, have push, have everything. Have is empty for you. Okay, finish. We start from the root node P, start from the root. This is a tree. Tree have the root. Okay, we already have stack. Okay, so if P is not equal now, it means this is not an empty tree. If it's empty tree, we cannot do anything. If it's not empty tree, we're gonna push T dot push the P, not P. Okay, Y S3 dot is empty. Y is not empty. Okay, so we're gonna pop. Okay, P equal S3 dot pop. Again, when we pop, we're gonna have the node, right? So we know it is a node. Okay, and then we're gonna visit m dot out dot print p dot id. Okay, so after we visit, we're gonna check if p dot right is not equal now. If there is a right child, we push right child first. Push. Put the p dot right. Okay. Else. Or not else. If there is a right, put right. Then if there is a left, put left. Okay. Okay. That's it. No, not much. Okay. St dot push left. Done. Okay. And then go to the main program. Call this one. Okay, let's say my tree dot pre-order iterative. Okay, I just put print line to separate something after this. Okay, so here the same. 150, 25, same thing. Understand? Exactly the same. You just translate, okay, from the book into the actual Java. The book also Java. Okay, when you run, you're supposed to get the same result. When you run. Okay. Done? Yes or no? Finish? Alan? Good. Finish? So, Iterative in order doesn't look like this. It's more complicated than this. You cannot just say, you just swap these two. No, it's not. In order doesn't work that way. And it doesn't work. It's a new algorithm. You cannot think the same way. Because, again, if you just swap them, what happened? Okay, if you just swap between visit and the right, okay, you just push the right, and then you visit that node already. Actually, in order, you're not going to visit that node until you finish the whole left subtree. Right? If you just swap this, it's not like recursion. Recursion, it will not move on if that one is not finished. Agree? But this is not recursion, it's a push. After you push, it continues. So if you just swap these two, it won't work. Understand? It's not the same with recursion. Recursion is different. Recursion said, if we haven't finished this one, it will not go this one. It has to keep recursive call, recursive call, recursive call until everything return all of them. Then we go back and continue. Okay, so the same thing with in order. If they keep recursive call until no more node to visit on the left, then it will visit that node. Okay, that's a recursion. Unlike this one. Okay, this one is not really recursive call. You just push one and continue. Okay, it's totally different. Not this mechanism, not this algorithm. Okay, all right, ready for in order? With the iterative, you have to rethink the whole thing. Not like this, different. That's why I asked you to write that one. Because I'm thinking how to write in order. And I just know how. I hope it works. All right, here, in order. I hope my idea is work. Ready? Okay, let me draw a tree. Here is a tree. Ooh, one more thing. When I draw over here, people over there, they cannot see me. Right? Okay, I'll do it over there. Okay, let's see what the tree look like. Let's say the tree have, just an example. What our tree look like? 100 and then what? I forgot. 100 and then we have 50. And then we have 25. And then we have 1. And then we have 35. And then 40. Hey, 40 here, right? And then 75. Hey, how come 35 here? Oh, okay. Now let me rewrite the whole thing. Where's my paper? Too much zooming. Okay, again. 100. And then what? 50. And then 25. 1. And then 35. And then 40. Like this. Okay. And then 75. And then 80. 98. Okay. And then this one have 200. And 200 have 199, 288. Okay, Let me have a few more for understanding. Let's see if I have, let's say, this one 60, and let's say this one have 55. Okay. All right. Here the in order. In order say we're supposed to visit the left first. Agree? After we visit the left, then we're gonna go to the right. Okay. So what we can do to push in the stack is, okay, you can push just only the, you go two direction, okay, go to the left, okay, you keep going left, okay, but we want to make sure that we keep track to go back. When we go back, we have to visit that parent. Agree? That is in order. In order, we keep going down, 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 down. When we get to the bottom, to the leaf, that it means we should visit that one. Okay, even though that one have the right, but we should visit that one. This is the in order. Agree? So we're gonna have two ways: going down or going back, going forward to the left or going back. Okay, when we go back, we have to make sure that where should we go back, which is the parent. Okay, and we want to make sure that when we go back, we're supposed to go to the right. Understand? Okay, so here we have two directions. Going down to the left. Why we going down to the left? We keep pushing that parent, that node. Agree? Okay. When it no more to go to the left, to go down. Okay, did it go down, go to the left only. Okay, why we moving left, we're going to push the parent, push the parent, push the parent, until we cannot go down any further. Agree? After that, we're going to go back by pop. Okay, when we move backward, we do two things. We pop and go to the right. And when we go to the right, we continue, move, push to the left. Okay? Again, if this one we cannot move to the left, then again we try to go to the left, and then we're going to continue with this one. And then try to go to the right of this one. Okay? We go to the, okay, we move back. With one we try to go to the left, and actually we cannot. We go back, we pop, okay, and then try to go to the right. Pop, go to the right. Okay, until we cannot go any further. Again, this one try to go to the left, nothing. We pop, and then kind of go to the right, and then after that we gonna pop. We pop this one. After we pop, we go to the right. Understand? We try to go to the left. Okay, this one again. This one have left. Now we gonna push 75 and go down to the left. Push. Okay. Every time that we pop, we visit that node. This is the in order. When we pop, we're gonna get the parent. Okay. For this case, we push only the parent, but we know that when we pop, visit the right. After we visit the right, we're gonna do the same thing. Push and keep move left. Go left, push, go left, push, go left, push. Actually, push first. Push, go left, push, go left, push, go left. Okay, until left is no further, and then we pop. When we pop to go to parent. When we pop, go to the parent, we pop and move right. And then we keep push. Okay, after we no more pushing, another word, when left is now, we go back and pop and move right. If right cannot go, we pop again. Understand the idea? Idea is we push only the parent. And then we keep, okay, going left, going left, going left. Push that node, go to left. Push that node, go to left. Push that node, go to left. After we push, and then if we have no left, then we pop. That's in order, because we cannot go left anymore. We pop, and then we visit. The node that we pop is the parent. After we pop, we're going to go right, because it is in order. If we haven't finished all the left, don't visit that parent. We pop and move right. After we move right, we do the same thing. We push that node, move left. Push node, move left. Push node, move left. Understand? Okay. Again, this is we pop, we push, push, push until we cannot push any further. Now we're going to start pop. And we try to go to the right. But if no right, we pop again. Okay, pop and try to go right. If you cannot go right, pop again. And try to go right. If you have right, now we're going to push. push this note and try to go left. But if we cannot go left, we go back. Okay, and then after we pop, we go right. Okay, and we try to push. Okay, we put this note first. Okay, if we cannot, we put and we cannot go any further, and then we pop. Okay, we try to pop. If we have right, we go right. If we pop, we cannot go right. We're gonna keep going back and pop again. Pop, visit that note, go right. Okay, every time we pop, we visit that note. We assume that what in the stack is parent only. Okay, understand? And whenever we pop the parent out, it's time to visit the parent. After visit parent, we have to go to the right. So we move pointer to the right. After we move pointer to the right, we're going to start to go left again. Understand? So the black one keep push. The blue one is the pop, go right. And then gonna push again, go left. And then pop, go right. Push again, and then pop, go right. And if we cannot go to the right, then we pop again. Okay, and then after we pop, we go to the right, and then we push. Okay, so the mechanism is, okay, push, keep pushing, push, push, and go left. Okay, loop, keep push, go left, push, go left, push, go left. Okay, until we cannot go any further. Okay, if left is now, another word. Okay, if left is now. Okay, now we're gonna pop and we're gonna visit. After visit, we go right. Okay, after we go right, we're gonna go back, do the same thing in this loop. Understand? Keep going left. Okay, but before we go left, we're gonna push that parent first, and then go left. Push that one, go left. Push that one, go left. Until we cannot push anymore. In other words, there is no left. If no left, then we're gonna pop and visit and move right. After we move right, think about this one note. We're gonna do the same thing in this note. We're gonna go left. Push, push, push. Because the pre-order keep going left. Until no further to the left, then we can visit that note. But we visit only when we start pop. Understand? So here this is what we're going to write. If we finish this one, we go home. In order. I hope it works. Okay. Iterative in order. Okay. Or in order iterative. Whatever you like. A big void in order iterative. We have to start from the root, and we also using stack. Okay, stack st equal new stack. Okay, P start from the root. Wait, not P. Again, we keep doing this. Why the it is not empty. Oh, but the first time we're gonna push first, otherwise it's empty. y stack dot is empty. Maybe it's not if p not now but if p is now then we can do it if p is not equal now if it now we cannot do anything. if the right is now, we gonna pop one more thing. Over here, when we go to the right, if the right is not down, okay, we're gonna go to the, for example, if the right is not now, and here, when we get to here, go to the right. If the right is not now, we're gonna go to the top of the loop, push that note, but we not visit, okay? But if the right is now, like for this case, if the right is now, we already visit this node. If the right is now, we gonna pop that node and then go to the right, okay? And if that node keep no right, have a long left, you're gonna keep pop visit. Okay, so here, over here we can go right at if the right is not now. If right is not equal to now, then we can go to the right. But if the right is now, we're gonna go to the loop. Visit, we keep pop, visit. Okay, so here, y p dot right, okay, is equal now. If p dot right equal now, if it equal now, we keep having now, we're gonna pop visit. In other words, if we have only the node keep going down, let's say for example, if this one is 19, okay, let's say 10, 5, like this, and we keep going back, okay, we try to go back, and the right is now. The right is now, we're going to visit. Go back, right now again, visit. Right now again, visit. When right not now, then we can go to the right. Okay, so did it inside the loop. Did it in this loop. If the right is now, we keep pop visit. Until right is not now. Right not now, then we go to right. Okay, and we go to right, we go to the top again and push this node. Okay, like when we go down here, okay, when right is not now, we go to the right. And now, when right is now, we don't go to the right. After we, if the right is now, left is now. And then we check if the right, if left is now, we pop first. We still need to pop and visit for one. No. We still need to pop and visit. If left is now, we still. But over here, we need to make a loop. If the right is now, we keep pop visit. Over here, we have we need to pop and visit for sure. And down here, Why the right is not now? Why p dot right is not equal now? We're gonna pop with it. Equal now, sorry, if it now. We pop with it until p dot right is not equal now. Then we're gonna go to the right and make sure that the queue is not empty. The stack is not empty. Stack is not empty. Okay, ready? If p is not now, we're gonna do push. St dot push. We're gonna push this p. After we push the p, we're gonna move p equal p dot left. After we move, we can move, but if after we move, if p equal now, in other words, left is now. Now we're gonna pop p equal, we're gonna pop, wait, not. Okay, after we pop, we're gonna visit. Okay, after we visit, now we're gonna go to the right if we can. If we cannot, we're gonna keep popping. So y stack is not empty, and p dot right is not equal now. It equal now. If it keep equal now, okay, if no right, then we're gonna pop and visit, pop and visit. But if p dot right is not equal now, when we get out here, p dot right is not equal now. Or if it's empty. Hey, not if, y, sorry. Y p not equal now, sorry. Hey, where is my y loop? Sorry, call it. I'm gonna have y here. Oh, I forgot to put y loop. Okay, I put y loop after this. This one, if the p dot right is equal, not equal now. Supposed to be not equal now, or maybe empty. If p dot right not equal now, then we're gonna do p equal p dot right. Okay, after p equal p dot right, we're gonna go to this push. Go over here. So this is a loop. stack is not now. It's empty, sorry. But at this time, my stack is really empty. At the first time, it's empty. Okay, I want to make sure that my stack is not empty, otherwise, at the beginning. Let me push some dummy. Okay, this is the general algorithm, would work like this. But the first time my stack is empty, my loop is not going to do anything. Okay, let me put some kind of in. This is not a good idea, but just having fun. Oh, maybe why P is not equal now. Sorry. Why P is not equal now? Okay, gotta move to the right. empty. Pop, repeat. Okay, okay. Oh. Click, we push that same note. Go to the right. Pop. Go back. Pop. No more. Okay, let me try. If it works, we go home. If it's not, we have to stay. It in order, iterative. Is it in order? Yeah, it is in order, but it something missing on the right. It's missing. Okay, we cannot go home. Okay. We pop. We pop. Oh, because we pop the root out. We pop the root out and make it now. The P dot right. We move to the right first. After we pop, I think this one we have to swap. The P dot right that we call now else. We pop. Pop all the way. If we pop, we flip. You're gonna keep pop. Hey-ya. Because when we move up, it could be equal to now. It's not empty. But when it's empty, A, B is not equal to now. When I get to here, my P still equals something. My P still equal to, at the end, right? We pop this one empty already. become P not equal to now. Or, not that. Not is not empty. What is that? P dot right not equal now. You're gonna move right. Right now the Q is half. That node. We pop, we visit that node. We get to the root. If P equal now, we pop. Not empty. T equal P dot right. Okay, done. Okay, I should not check this one. Okay, we go to the right even though it's now. The condition is even though it's empty. Sorry. When we come to here, okay, we're gonna pop, right? After we pop, we visit this node. Okay, after visit this node, okay, we're gonna go to the right. You can see that. Okay, before we go to the right in our program, after we go to the right, our while loop said y is not empty. At this time, it's already empty because we already popped the root out. Okay, so the condition is if it's not empty or we have the right. Okay, so if we have the right, then we go to the right and then we push. Okay, unlike this one, when we finish the whole thing, okay, now after we pop with it, we move right. Right is now, and the queue and the stack also empty. Okay, so we finish this one when nothing in the stack, and the right is now. But let's see like this one. This one we still have the top. That one still in the stack. That's why we go there. But when we get to there, now the stack is empty, but we still have right to go. Okay, so it's like this. We don't have this condition. We keep going right, but if the right is now, okay, and also the stack is empty, we terminate. Right, for this case, we already pop everything, pop visit, pop visit. When we get to this, when we get to the rightmost node, we already pop everything out, and the right of the rightmost node also now. Okay, so no checking here. We move right anyway, even though it's now. Okay, and that's in order. Okay. The start is a little bit tricky because we checking if it's, actually we don't have that one because at the beginning is the root anyway. Oh, we don't need this one. We have the root. It's not now. Hey, let me comment first. It doesn't work. We don't really need that. Yeah, we don't need that. Okay, from the beginning, P is point to root already. We don't need that if, not that start. From the beginning, P is at the root, so root is not now. We're going to get in for sure. Again, when we see the node, okay, we move down, poof, and move down to the left. We keep move down to the left. Okay, until we cannot move down anymore, P is now. When P is now, we cannot move down anymore. When we cannot move down anymore, okay, now we're going to start to move up. When we move up, we do two things. Number one, we pop. Number two, we sit. Okay. After we visit, we move right. Move just one time, right? And then after that, to the top of the loop again, we push that node, right node. Okay, this one is we move up. Move up. How do we move up? We pop. When we pop, we move up. Okay, we move up by, we pop the node out, then move up. And then we visit that node. That's the parent. Because in order, we're going to move from the left to the parent and then visit the parent. Okay. Stack store only parent node. Parent node is in a node that have child or children. We never start not really true. We start just not really parent, even though the leaf node. But we imply the parent, even though we have leaf node. We have no node. But we store, after we store, we come back and we're going to pop. Okay, but imply that we gonna push the parent before we move to the left. And we pop, we get to the parent. Okay, done. Right, go home. Understand or not? Complicated. I mean this part, okay, is the part that keep going left. We push in the stack so that we keep going left. Okay, this top part, okay, is a part that we keep going left from the root. Keep go left, keep go left, keep go left. Okay, we keep going left, but without visiting. Okay, because when P is not now, okay, we're gonna visit only when it's now. If it's not now, we do only that two things, and then go to the top. We keep go left only, because it is in order. In order, we will visit that node. We will not visit that node until we go to the left all the way. Until no left, then we're going to start visit that node. This is in order. In order that you have to go to finish the left first before you visit that node. This is in order. In order is supposed to do left, that node, and then the right. That's why we keep going down to the left without visiting. Actually, when we have a tree, okay, we're going to keep we're going to keep moving down left without visit at all. Okay, until we cannot go left anymore. Here, when P equal to the now, we go poof here. It will be no left. Now, when we have no left, now we're going to start pop this node out and visit. Okay, after we visit this node, we must go to the right. Okay, and again, when we go to the right, we will not visit if this one have the left. We're going to keep go left without visiting it until we cannot go further. Okay, let's say this is the last leftmost node of this subtree. Then we're going to come back and visit this one, and then we're going to go right. If no right, we're going to go back. Okay, so this one said, if we have no right, right is now. If right is now, we're going to go back, pop, and then visit that node. If right is now again, go back, pop, visit that node. Okay, if this part, if they have a long left, okay, we're going to go back, no right, visit, no right, visit, no right, visit. If there is a right, we visit and then go right. And again, when we go right, we're going to do the same thing, go left. Okay, go left until no more left, and then go back, visit, and try to go right. If we go right, if it's not now, we not going to visit, we're going to go left until we have no left. Understand? No. Hả? Xong. Hả? Send the whole thing. Again, okay, let's see, I have 100, 50, 200, 30, 70, 60, 20, 25, 10, 2. Let's see, for example, look at my algorithm, okay? Okay, if you look at the program, okay, we start P at the root. Here, this is a P, okay? This is in order. What we want for in order? We want to visit left, right, left, that node, and right. Agree? We will not visit that node if we haven't finished the left. Okay? That's why my program, okay, when I see the node, I'm not going to visit. I'm going to push. Okay? So now let's see. The first time, okay, I start from P, start from root. Okay, I'm not going to visit this one. I'm going to push this one, 100, without visiting it. Okay? Without visit, just push. And then I move left. Okay, after I move left, should I visit? That is in order. We will not visit if as long as we haven't visited the left. So we're going to push again, 50. Okay, without visiting it. Okay, I have nothing left yet. And then I'm going to move left again. Okay, and then I push again, push 30. Okay, and then you can see that this one keep doing that because my P is not now. Okay, my P not now. I'm going to keep pushing 20 in here. Okay, and then again, this is still not now. I'm going to keep move P. P is not now. Okay, if P is now, I'm going to do something. If P not now, I go to the top. Keep pushing. I'm going to push 10. Okay, and then move P. Okay, and then it is not now again. I'm going to push these 2. Without visit the 2. Okay, and then I'm going to move P now. Now, after I move P equal P dot left, now my P point to now. Okay, now it means that I have no more left. When I have no more left, now this thing going to start. Okay, I'm going to start visiting because I have no more left. So what I do is that I'm going to pop this one out. Okay, after I pop, I visit. So this is the first time that I visit. 2. Okay, pop and visit. Okay, now after I visit, okay, in general case, after I pop, I visit. After I visit, I try to go to the right. Okay, okay, that's the rule. Okay, because every time that you pop a node, you're going to go to the right. If you pop this one, you're going to start moving right. Okay. So I pop, I visit, and I try to go right. So here I pop, and I try to go to the right. However, for this case, I try to go to the right. Okay, now, this queue is not empty, but my right is now. If my right is now, what should I do? I have nothing to push. I'm going to keep doing this. This one, if my right is now, I'm going to pop another one. Okay, if my right is now, I'm going to pop and visit. Okay, this one, okay, again, my right is now. I'm going to pop 10. Okay, after I pop 10, my P right now point to here. This my P now. Okay, I'm going to pop this one now, and then I'm going to visit that node. After I visit that node, I try to check again, my P dot right is still now or not. If my P dot right is still now, I pop again. Because this one is still now, I pop again. I'm going to pop this 20. Okay? After I pop this 20, now my P is here. Okay? Now, after I pop 20, my right is now? No. If it's not now, okay, I'm stop this while loop. I'm going to move my P, not visit. I'm going to move my P here. It depends, I visit or not, depends that I have left or not. Okay, so here, after I move P, if I have the right, okay, I'm going to move P to here. After I move P, what I do? I go back to the top. I'm going to push. Because I don't know yet I have left or not. right? Let's see, you don't see it down here. We don't know we have left or not. We're going to push first. Whatever we get to a node, we push first. For this case, I'm going to push 25. Okay? After I push, I'm going to move left. Okay? After I move left, now, do I have left? No. If I don't have left, then I'm going to go in here. P equal now. Again, if I don't have left, what I do? If P equal now, I'm going to pop and visit. Okay? After I pop and visit, okay, I'm going to check whether I have dot right or not. Okay, again, I pop visit. My stack is not empty. My right is equal to now. Okay, if my right equal to now, what I do? I'm going to pop again. Okay, if my right equal to now, I'm going to pop. Okay, so now I'm going to pop 30, pop and visit. I keep pop and visit, pop and visit. Okay, so now after I pop this one, I visit. After I visit, again, I go back. My right is now. Yes, my right now again. If my right is now, I'm going to pop and visit. Now my P is here now. Okay? When my P is here again, it means it implies that I already finished all this left. I'm going to do the same thing. I'm going to pop and visit. Hold on. After I do this, I pop and visit 30. I go back here. Now my right is now. No, my right not now. Okay, but I already pop and visit that 50. Okay, I already pop and visit that 50. My right, actually, it can turn off. Okay, so now after I pop and visit 50, now my right is not now. If my right not now, what I do? Okay, I'm going to move right. So now my P equal P dot right. Okay, again, after I move my P here, I'm going to go to the top of the loop. What does the top of the loop do? Push. Why I have to push and go left? Because again, after I move here, I don't know that I have my left or not. Okay, if I have my left, I must not visit this. That's why I push first. Push 70, okay, and move left. P equal P dot left. Okay, and again, since did it not now, okay, if it not now, it means, okay, we have to keep pushing this one. Okay, so we're going to push again. We go to the top of the loop, P is not now. We're going to push this 60, and P equal P dot left. Okay, now my P is now. It means no more to the left. If no more to the left, it means it's time to visit that node. Okay, so here when my P is now I'm going to pop and visit. Okay, so look at my stack. I have 60. I'm going to pop 60 and visit. Understand? Okay. And again, after I pop and visit, okay, I check by my P dot right equal now. Yes, my P dot right is 3, my P is here. Okay, after I pop, okay, my P is going to point here. And then visit. After I visit, I check P dot right equal now or not. For this case, my P dot right now. If my P dot right now, I'm going to pop 70. Okay, and visit 70. Understand? And then what next? Now again, after I pop and visit, my P dot right equal now? No, if my P dot right equal now, I'm going to stop this one and I'm going to go down outside this Y. I'm going to move P dot right. So P dot right is here. Again, after P dot right is here, what should I do? The first time, okay, we're going to go push. AD. Okay, after I push AD, P on the top, I push AD, and then I move P equal P dot left, so my P is going to move here, which is now. Okay, again, I move here because I want to know I have left or not. If I have no left, it means it is in order. It's time for parent to be visited. Okay, so that's why we pop and visit. Okay, pop and visit. Understand? Okay. In other words, what in the stack is, I implied it is like some kind of parent stack. Because when it pop, it's going to be the parent of that one. Okay, the parent of the P that we just get out. Okay, or when we are here, we have no right. When we pop, it's going to be parent. Okay, if it's no right, when we pop, it's going to be parent. Okay, but again, when it's here, when we pop, I go there because we already visit that one. Okay, again, after I pop AD, okay, now I visit. After I visit, do I have dot right? Yes, I have dot right. I'm not going to go in this loop. I'm going to go P equal P dot right. After P equal P dot right, I move to the top. I'm going to push. Okay, I push again. Okay, I put first. Every time I go to that node, right, I move. Either move right or move left, I have to push. But after push, I check whether I have left or not. Sorry, after I push, I move left. Sorry, after I push, I move left. After I move left, if it's now, then I'm going to start to pop. And I just put this one. So if I pop, I'm going to get 90. I pop, I get 90. Okay. It is a pop. Pop and visit. Okay. After pop, visit, we're going to check whether right is now. Is it right now? Yeah, it's right now. What we do? It is a bit while loop. If right now, we're going to go back and pop again. And here the key, after I pop, again, if the right is now, I pop and visit. This is the part that I have error. After I pop, I pop. Okay, this is the right, have now. I pop and visit. After I pop, my P is where? 100. Okay, I pop 100 out and I move my P to that 100 and visit this 100. At this time, my stack is empty. At the beginning, I don't have the second condition. I have only the first one. That's why my program stopped here. But actually, we know it's not finished yet. Okay? So that's why I add, my while loop will terminate. Either stack is empty or both. Okay? Stack is empty and P is now. It's both of them. Okay? If stack is empty, but my P is not now, I still keep going. This case, stack is empty now. But my P is not now. Still point here. I keep going. Okay? Understand? Okay. Again, after I pop, I visit 100. Okay? Sorry. After I pop 100, I visit 100. After I visit 100, no, not yet. What I do? I'm going to move P equal P dot right. Now, when my P equal P dot right, my P is not now. In other words, when I get to the root, my stack is empty now. But since the root still have right, I keep going. Okay, so the second condition is still true, not now. P is not equal now. So then I'm going to go in here, but again, the first time get in here, we have to push. Okay, so I'm going to push this 200. Okay, and then move left. Now, when I move left, what happened? It's now. Okay, when it's now, I'm going to get to that if. I'm going to pop. Okay, if it's now, I pop and visit. After I pop and visit, now what happened? When I pop and visit, my right is now or not now? My right is, but my stack is empty. At this time, my stack is empty. You can see that. So if my stack is empty, nothing else for me to pop. Okay, so this one will be false, and then I go here. P equal P dot right. Down here. Okay, now my P equal P dot right, I go to the while loop. It is not empty. No, it is empty. My P is not now. No, my P is now. And at the time we finish the whole thing. Nothing in the queue, nothing in the stack. P is outside the tree. Okay, but again at this time, stack is empty, but my P is still not now. Understand? We keep track the parent in the stack. Okay, but again the idea is we keep going left, but without visiting. Until cannot go left anymore, we go back, pop, and visit. Okay, and after we visit, can we go right or not? If we cannot go right, then we pop and visit. Cannot go right, pop again and visit. Can go right, then go right without visit, because when we go right, the right may have children. When we go right, we go to the top of the loop, push first. Okay, after we push, we go left. If we cannot go left, it means now we have to come back, pop, and visit. Understand? And we cannot go left anymore, we pop and visit that node and try to go right. And if that right node have left, I keep going left again. Okay? All right. Good night, everyone. I see you on Friday, which is tomorrow at 4:30. Okay, tomorrow we're going to go a little bit faster. Okay? What else that we haven't learned about the tree? We learn how to add a new node. We learn how to search the node on the tree. Okay, we learn how to travel to every node on the tree. Okay? Now, insert we already did. Now, we need to be able to delete the tree. Delete the node from the tree. And that is a little bit complex. I show you tomorrow how to delete. For example, you delete this 70, what happened? If I delete this 70, what happened? Question is, who would be the child of 50? If I delete this node, who would be the child of 50? What happened to 80? 80 will be the child of 60. Okay.